Today, I'd like to talk about the seismic inspection of existing structures based on the amount of their deformation due to liquefaction. In structures with very long lengths, such as river dikes, have not been constructed with liquefaction in mind, it is necessary to extract, repair their parts that could be easily damaged in the future earthquakes. In inspecting their structures, it's necessary to quantitatively estimate the point where countermeasures are required based on the amount of settlement or uplift of the structures. For that purpose, it is necessary to properly consider the process of the settlement or uplift of the structures based on the past cases of damage or result of model tests, and develop a method to easily estimate the amount of settlement of uplift. In Japan, there are many cases of structures damaged and many model tests using shaking table tests have been conducted. Simple estimation methods have been developed and based on these, and are being used for inspections. Furthermore, measures are being taken based on the inspection result. Therefore, I'd like to introduce the current status of efforts being made in Japan for embankments, low-rise housing, and sewer manholes. First, embankments. In the case of river dikes, it's a serious problem that river water overflows into the adjacent areas when the dikes subsided. However, even if subsidence occurs, countermeasures are not necessary if the top of the river dike is higher than any probable river water level. In the case of railway and road embankments, as long as subsidence does not prevent trains or cars from crossing the embankment, countermeasures are not needed. Therefore, for long embankments, it's necessary to easily estimate the distribution of subsidence during the future earthquakes, and to determine the property of the locations where countermeasures will be taken. In Japan, as there are more than 30,000 rivers and the seismic activity is high, some river dikes have been damaged every time an earthquake occurs. These damaged river dikes were usually restored just by filling the dikes with soil again. And earthquake countermeasures were hardly taken until the 1995 Kobe earthquake. However, the Kobe earthquake caused the Yodo River dike to subside significantly, and the largest city of Osaka was about to be flooded by river water. Therefore, since then, many river dikes have been subjected to seismic inspection and seismic retrofitting. Roads and railway embankments are less damaged by liquefaction than river embankments, but have been damaged by the 2011 Tohoku earthquake and other earthquakes. Let's show an example of a large shaking table test in which the mechanism of the subsidence due to liquefaction was investigated by Public Works Research Institute in Japan. This figure shows the time history of excess power pressure measured by 38 pressure transducer. The vertical broken line in each time history indicates the time when the shaking is over. If the inside of the ground is roughly divided into 4 zones A, B, C, D, the time history of the excess water pressure was different in each zone. This figure shows the time history of the subsidence of the crest of the dike. It gradually subsided from the start of the shaking. Judging from these, it is considered that the pore water pressure increased and decreased as the dike subsided according to this process. Pour water pressure increased in the BCD zone with the start of shaking. The dike began to slip and subside began to occur in the C zone. The excess pressure decreased once because of the positive dilatancy due to sliding, and then increased due to the propagation of excess pressure from zone of B. Since the effective confined pressure in D zone was smaller than the excess pressure than other part, the excess pressure rose less in D zone than in BC zone. However, the pore water pressure increased even after the shaking was ended due to propagation from the B, E, and C zones. In analyzing the stability of the dike slope, the safety factor for sliding Fs can be expressed by this equation, considering the horizontal seismic force and the excess pore water pressure delta U. If Fs is small, the amount of subsidence of the dike may be large. As mentioned above, the time history of the excess pore pressure in the ground is complicated, and it is necessary to obtain the distribution of excess pore water pressure in the cross-section at a certain point in time and consider it in the calculation. However, since this is time-consuming, it is a common practice to simplify and estimate the distribution of excess pore water pressure from the distribution of safety factor against liquefaction FL, ignoring the time history of excess pore water pressure. After the 1995 Kobe earthquake, using this simple method, the safety factor Fs for slide was calculated for 27 river dikes damaged during 6 past earthquakes, and compare with the settlement ratio of the dike as shown in this figure. In the calculation, both the safety factor FSD, when only the excess water pressure is considered, and the safety factor FSKH, when the only horizontal seismic intensity is considered, are calculated, and the smaller one is shown in this figure. Although the plotted points are scattered, the settlement rate increased as the safety factor decreased. Therefore, based on the upper limit shown in this figure, damage to river dikes due to the level 1 seismic motion have been inspected, and countermeasures have been applied in Japan. After that, it became necessary to investigate the seismic resistance against level 2 seismic motion, design countermeasures if necessary, and implement the countermeasures. In order to estimate the amount of subsidence of the dike here, instead of the indirect method of estimating from Fs, methods of directly analyzing the deformation of the dike have been adopted. The optimal analysis method is two-dimensional seismic response analysis that can be considered liquefaction. However, since this requires detailed soil test and costly analysis, the applicability of the simple static method was examined. Then ARIT was taken as a static analysis method, and it was used to design countermeasures that were included in the guidance in 2016. This figure shows the result of the reproduction analysis of the river dike damaged by the Kobe earthquake. As shown in the schematic diagram in the figure, the guidance cover 4 countermeasures. These methods were designed by analysis using ARIT, and currently measures are being taken according to this guide. Railway embankments are compacted well while being constructed, so excessive poor water pressure is unlikely to occur in the embankments during an earthquake. Therefore, it is considered that the shear rigidity of these embankments does not decrease during an earthquake, and that decrease in the shear rigidity of the ground and the weight of the embankment cause subsidence. Then a method for estimating the amount of subsidence was developed based on the result of several previous shaking table tests. These figures show the relationship between the liquefaction potential PL and the settlement ratio. The relationship have been introduced in the railway construction standards and are used to estimate the amount of embankment and subsidence due to liquefaction. Next is low-rise housing. When the ground liquefies, it's often so low-rise houses settle into the ground under their own weight and tilt. The ground also subsides due to volume shrinkage as excess water pressure disappears after liquefaction occurs. Therefore, it is necessary to distinguish between total settlement, penetration settlement, and subsidence of the ground. Among them, the penetration settlement greatly affects the damage. Low-rise houses suffered less subsidence and inclination due to liquefaction than mid-rise buildings, and did not appear to be greatly damaged. So damage to low-rise houses has not received much attention in Japan. However, during the 2000 Totoken-Seiba earthquake, it became clear that even a slight tilt would cause health problems such as dizziness and nausea. Therefore, 2 months after the Tohoku earthquake, the Cabinet Office provided new criteria shown in this table for judging the degree of the damage from the amount of settlement and the angle of inclination. This figure shows the relationship between the amount of penetration settlement and the inclination angle measured in 4 cities after the Tohoku earthquake. In order to investigate the process of the settlement and inclination of low-rise houses, many shaking table tests and the analysis of disaster cases have been conducted. Regarding the process of the subsidence, an experiment was conducted by placing a large laminar soil container on a large shaking table after the Tohoku earthquake. Please watch the right side model house. So it gradually settles. But we cannot see the unejected. So these figures show the time histories of water pressure ratio at this case. At 2 points here, there are pressure increase as shown in this figure and reached to the maximum value. So it means liquefaction occurred at almost 5 seconds. But the water spilled out at the edge of the model house after the end of shaking. And excessive pressure measured at just under the model house increased slowly and reached the maximum value at 30 seconds. This figure shows a time history of penetration settlement. The settlement started from just after the occurrence of liquefaction and increased gradually. Based on model tests, the author concluded that the house does not sink into a hole that was produced by spilling out, but penetrates the ground due to the decrease in shear modulus of the structure layer. And the ground surface settled slowly because the liquefied layer and around the house densified gradually due to the spilling out of the water. Regarding the process of tilting and houses in a densely populated urban area, there was a tendency to tilt inward when two houses are close each other, as shown in this photo. The tendency was also obtained by analysis. This figure shows an example of analysis by Arid. The direction of inclination and the angle of inclination differed depending on the distance between the two houses. In Japan, although many low-rise houses were severely damaged by the Tohoku earthquake, measures to prevent liquefaction damage are not being applied for new houses for three main reasons. The first one is such measures are not required by law for low-rise houses. Second, the possibility of the housing damage due to liquefaction is not fully recognized by the residents and the house makers. Third, the problem damage to houses cannot be estimated correctly from the liquefaction hazard map currently being created. Therefore, as I talked in the oral presentation the day before yesterday, the EMRIT issued a liquefaction hazard map guide for risk communication in order to promote the adoption of the countermeasures. This guide suggests the following procedure to easily estimate the probable amount of penetration settlement and the angle of inclination of a house. First, the local government creates a liquefaction hazard map specialized for low-rise houses. Residents and the house makers look at the hazard map, and if they are in gray zone, conduct a simple soil investigation, such as screw wedge sounding, to estimate the depth of distribution of FL. In the sounding, collect the soil and measure the groundwater level. Sounding cost is about $1,000 US. Then a house maker calculates the amount of penetration settlement of the house based on the Steinbrenner's method, but the shear rigidity of the liquefied layer is estimated from the value of FL by the relationship used in Arid. Next, estimated the inclination angle from the amount of settlement based on these figures, depending on the density of the houses. Finally, residents and house makers will judge the degree of likely damage based on this table and take measures if necessary. The last one is the sewer manholes and the pipes. Many sewer manholes and pipes were buried deeper than the groundwater level. And since these apparent unit volume weight are light, liquefaction makes them easy to float. In 1993, sewer manholes and pipes were uplifted, as shown in this photo, in peat ground that was not liquefied by Kushiroki earthquake, which surprised Japanese researchers. When the damaged site was excavated and investigated, it became clear that the sand backfilled after the excavation and installed the manhole and pipes had liquefied. The 2003 Tokachi Oki earthquake also caused the uplift of many manholes. Of these, in Ombes town, the extent of manhole rising varied greatly depending on the location. And while manholes along BB dash line surface more than 60 centimeters, those along A dash line did not surface at all. When the cause was investigated, the former was clay ground and the latter was sandy ground. The 2004 Niigata-ken Chues earthquake caused the uplift of about 1,400 manholes. Based on these cases, the authors considered the influence of surrounding ground on the amount of the rising, as shown in this figure. Severe uplift occurs in clay or peaty ground. On sand ground, even if it liquefies, only a small amount of uplift occurs. This photo shows a car collided with a manhole that floated during the 2004 Niigata-ken Chues earthquake. Therefore, the impact of the rise of shear manholes on the lives of the residents is not only the sewage water cannot flow after the earthquake, but also that the manhole became an obstacle to traffic. They can be particularly serious obstacle when residents have to evacuate in an emergency due to a fire or tsunami caused by the earthquake, or when emergency vehicles have to pass through. For example, when a hearing was held with the staff of the fire department, they answered that they cannot pass if it rises from the road surface by amount 10 centimeter to 20 centimeter, as shown in this figure. After the Kushiroki earthquake, the author and his colleague conducted tests in which a small soil container was placed on a shaking table and vibrated in order to investigate the process of uplift of manholes and buried pipes. Since the front of this soil container was made of glass, udon, it's a Japanese noodle, udon chips were installed at a constant interval between the glass and the ground. Then the movement of the soil particle was estimated from the displacement of the udon chips. Tests were conducted under many conditions by changing the width of the backfill soil and the groundwater level, etc. Among them, the time history of the model is shown in this figure, and the movement of udon chip at 2 stages are shown in this figure. In each case, the manhole floated gradually as the surrounding soil wrap it. The safety factor against uplift due to liquefaction effects can be calculated by the balance between the weight of the structure, the friction force with the ground, and the floating force. This figure shows how to calculate effects for sewer manhole and utility tunnels in Japan. This safety factor determines whether or not these structures float. However, if this value is small, it can express that uplift displacement will increase. Then Koseki et al. Calculated the effects for manholes that uplifted during the Kushiroki earthquake and compare it with the observed uplift displacement. This figure shows the result when the calculation is performed, assuming that the backfill soil was liquefied. As can be seen in this figure, no clear relationship was found between the two. In Japan, measures that were measures are being taken to prevent the manholes, such as placing a weight on the manhole and dissipating excess water pressure near them for existing manholes varied in major roads. However, it is difficult to select the place to take measures and decide the priority. This is because the manhole lift caused by the liquefaction of backfill soil does not rise significantly when surrounding ground liquefies. In other words, the liquefaction hazard map cannot be used to select the location where countermeasure will be taken. Further research is needed. So, concluding remarks, the current situation in which inspections are being conducted in Japan that requires countermeasures against liquefaction, targeting river dikes, railway embankments, low-rise houses, and sewer manholes is introduced. The Ministry of Land Infrastructure, Transport, and Tourism is inspecting river dikes and taking measures. As for low-rise housing, an inspection guide has just been created, and since residents and house makers are not aware of the damage caused by the liquefaction, it is necessary to promote the adoption of countermeasures. Measures against uplift of manhole are being taken for existing sewer manholes, but inspection methods still needed to be developed. Thank you for your kind attention.
Thank you very much for a very interesting and excellent presentation. I'd open it up. It looks like we would have time for a couple questions maybe. And then possibly after the second keynote speaker, we could follow it up if there's additional questions. If you're able to unmute yourself and just ask the question, that would be good, because I'm not sure how to necessarily see if someone has their hand raised. In the absence of anybody else, I have a question. You had showed the shake table test with improved ground and unimproved ground, and it showed the unimproved ground with the simulated house sinking. For the improved ground, it showed that you had sheet pile walls. Could you explain what the sheet pile walls were? Were they around the perimeter, or were they bearing any, were they just isolating the soil underneath the foundation, or were they bearing any vertical load?
Okay, as time is limited, so I didn't explain this one. But the idea is if the liquefaction occurred inside this sheet pile wall, the soil does not move to the upward. So we conducted the test, not reach to the dense sand, but also the half depth of the sheet pile wall, even though the countermeasures are affected. Can you understand?
Yes. So
it means the idea of the countermeasure is not to move the liquefied soil outside.
I see.
Okay.
So it's to encase the liquefied soil and prevent it from moving laterally. And so
yeah. Yes.
Okay.
Yes, the idea is this one.
Okay. Very good. Very good. Are there any other questions?
Hi, Ross. I'll just follow up on that same theme, if I may. I guess my question is, putting the sheet piles below houses sort of constrains the soil so it can't go anywhere, and you create a nice stiff column that the house just sits on. But it's difficult as a retrofit solution. Have you got evidence to show whether it works if you sort of have a series of houses and you can sort of put a ring around a bunch of houses, maybe a block or so on, and sort of constrain the soil within that, and how big that area can get before essentially you start getting problems within the block?
Well, I'm sorry, I cannot understand what you mean. So, yeah, okay, we installed this sheet pile outside of the house, and because this can be applied to the existing house, not only the new house. So it's a merit for this countermeasure.
I see. And okay, so thank you. And then if you were to try and, if you had maybe 4 houses close together, can you put a boundary around 4 houses, or is it basically on a house by house basis?
Okay, this is only individual houses, not surrounded by the an area.
Yeah.
It's okay.
Okay. Thank you.
Thank you very much. If there are any other questions, we may be able to get to those after the second speaker, but with this, we will turn it over to the second speaker.
Thank you very much.